Hello everyone, this is Mr. Couple. In this video, I'll be talking about stellar nucleosynthesis, which is the process by which matter is created inside stars. Before we start talking about stars, I wanted you to get an idea about the size of stars. So I'm calling this a stellar size comparison. This image was taken from Wikipedia Commons. The step one we'll look at is the inner rocky planets in our solar system, Mercury, Mars, Venus, and Earth, and they're sorted based on their sizes. And then what we'll do is each time we're going to take a step out and we're going to look at larger and larger objects. So as we move over, we'll look at the outer gas giants. So here's the Earth, and notice how small the Earth is in comparison to these much larger planets. We can go even further. So here's Jupiter next to the Sun. This is the Sun right here. And here's Sirius, which is the brightest star in the night sky. And we can go even further. So now Sirius is that little tiny star on this left-hand side. Notice how large these other stars are. Pollux, Arcturus, Aldebaran. They're just some massive, massive stars out there. And these guys are tiny compared to the biggest stars out there. These stars are called red giants or red supergiants. And this is what a star does at the end of its life. It turns into this massive, massive, massive star. And these are the largest stars that exist. In fact, what astronomers usually do is we create this chart. It's called a Hertzsprung-Russell Diagram, or an HR diagram, where you plot the luminosity of the star, which is roughly the power output, the energy that it puts out, against the surface temperature of the star. And you find that there's sort of a pattern of where you find these stars of where they lie. So there's this main sequence, which is where most stars are found in the middle stages of their life. But as stars evolve, they actually will move off this main sequence and become red giants, and then they'll die and they'll come back down and end their lives down here as white dwarfs. So stars do a lot of really cool stuff, and that's what I want to talk about in this video. Is I want to briefly just discuss what goes on inside a star and explain how stars live and how they die. This is a really cool picture of a telescope in, I believe it's in the Atacama Desert in Chile, and they're pointing this laser at the center of our Milky Way galaxy. And so there's all these high-powered telescopes on the ground and in space that have taken these beautiful, amazing images that just help us understand and reveal our place in the universe. This is a photograph of a galaxy. Galaxy is a collection of hundreds of billions of stars. And so each speck of light here is a individual star. You'll notice that there's such a high concentration of stars here at the center of this galaxy that you can't even see where the light from one starts and the other one ends. There's just millions upon millions of stars, billions of stars even, in this photograph. And so it's important to realize that each of these stars could have a planet system around it. So a galaxy is a collection of stars. Here's a sideways view of a galaxy. So this is an edge-on view. So this is a spiral galaxy, but we're viewing it from the side. And you'll notice that there's these areas that are not transparent, these areas that block out light. And that's what I really want to look at. We've also taken images of galaxies crashing into each other and colliding. You can see these bright, violent red spots. Those are regions where matter from one galaxy is colliding with matter from another galaxy. And it's usually these dark spots that we see. So this is a computer simulated image of what we think, our best guess, of what we think our own galaxy looks like. This is where the sun is found in the Milky Way galaxy. And you'll notice again that there's these regions where there's some red lights here. And each of these regions is an area of star formation. So where you see these red spots, those are areas where stars are being born. And stars are born inside what are called nebulas, which is a giant cloud of gas. And here's a picture of the Hubble Space Telescope zoomed in on the Carina Nebula. So let's just look across here. The part that I want to focus in on is over here on the right-hand side, because something really awesome is going to be revealed to us over here. So let's look here to the side. It's this area here. So we'll go ahead and zoom in and rotate it and take a nice closer look at it. And this is a stellar nursery. And so when stars are created, they're created from the collapsing dust clouds in space. So like these nebulas, it's just clusters of matter. They're slowly brought together by the forces of gravity and they collapse in on themselves. And so stars are created in these dense areas where gravity collapses. So this is a stellar nursery. So you can see these little balls that are sort of like tendrils like coming off the side of this cloud. These are all regions that are going to become stars. So what fuels a star? Like, where does a star get its energy from? So if you look at the star, there's actually three main regions of the star. There's the core, which is where the energy is coming from, the radiative zone, which is where the energy comes out from the core, and then the convective zone, which is where the energy is, through convection, released, cycled up to the surface of the star and then out from the surface of the star. Deep inside a star's core, the temperature and pressure are so high from all that gravitational pressure pulling all that mass together that hydrogen is fused together to make helium. So when a proton is alone by itself, the mass per nucleon is quite high. But if we can get that proton to turn into helium, you can actually lower the mass of that proton. So a proton, when it's inside a helium nucleus, has less mass than when it's by itself. And we know that this process releases energy. So the fusion of hydrogen releases energy. And this is what the sun is doing. It's called the Proton-Proton Chain. So what the sun does is it takes two protons and smashes them together at extremely high speeds, which is because of the high temperatures, millions of degrees inside the core. These hydrogens smash together, and then immediately one of them will beta decay into a neutron. And then that's where that neutrino and the positron are coming from. Then you just have to find this is hydrogen 2 now, will smash into another proton, and then that will create helium-3. And then somewhere else in the star, the same process is occurring in parallel to this. And now you have two helium-3s. And then they smash together, shoot out two protons because it's not stable with those two. Those two protons get ejected. And then you end up with beautiful helium-4, nice and stable. And this process, at each step in this process, is releasing energy. And that energy is fueling the star. So every second, the sun takes 600,000 tons of hydrogen and turns it into 596 million tons of helium. Did I say 1,000? 600 million tons of hydrogen per second, turning into 596 million tons of helium. And that's each second. That's just insane. So that means that 4 million tons of matter is lost. So every second, the sun is getting 4 million tons lighter because that mass is being turned into energy. And if you do this calculation, this is the kilogram amount of 4 million tons is equal to 3.6 times 10 to the 9th kilograms. If we take that and plug it into E equals mc squared, we get this number. This is the luminosity of the sun. This is the energy output of the sun. The sun outputs 3.24 times 10 to the 26 joules. And so that's in 1 second. So you could say this is the wattage, like 10 to the 26 joules per second that the sun is releasing. And so this amount of energy that the sun releases in 1 second is more energy than humans have used in all of human history. The sun outputs more energy in a second than humans have used in the entirety of human civilization. That is a ridiculous amount of energy. And this is the power of nuclear fusion. Normally, the forces acting in a star are in equilibrium. You have the inward pull of gravity, that's the mass of the star pulling itself inward, and you have this outward pressure from the radiation or from the energy radiating from the core pushing out against this gravitational collapse. And these two forces balance and allows the star to reach an equilibrium. But if a star runs out of hydrogen, that thermal pressure shuts off. And then what happens? The star collapses. And as the star collapses, it becomes even hotter and there's even higher pressures. And then the star starts to fuse helium into carbon. And when this happens, an outburst of energy called a helium flash happens, and the star just begins to grow and expand and becomes massive, and it turns into a red giant. This is the process that happens inside red giant stars. Is they're hot enough now that this repulsive force between two protons can be overcome inside this denser, hotter core, and it actually starts to fuse them into beryllium and then grab another helium and fuse that into carbon. This is called the triple alpha process, where you're creating carbon. And all the carbon-12 in the universe was created this way. That all the carbon-12, and carbon is an essential element that you need for life. The ingredients of life were created inside red giant stars. In about 5 billion years from now, this is what's going to happen.
Deep inside the sun, the last of its hydrogen fuel is consumed. What remains is a core of helium. It takes enormous pressure and heat to make the helium fuse. But now, the immense force of the sun's outer layers bears down, and this fusion begins. The powerful ignition actually propels parts of the sun out into the galaxy. As the sun continues to expand, the Earth is eventually baked in 3,600-degree heat. Our planet is scorched smooth. Its relentless growth has brought the sun just a few million miles from Earth. It has already swallowed Venus and Mercury. Now the rising sun completely fills the horizon on what remains of our planet. It's over 200 times bigger than it once was.
In 5 billion years, the sun will destroy the Earth. This is an artistic rendering of what that might look like. Or you see the Earth as this molten, melted chunk of melted rock because the sun is so large and so close that it just starts to completely melt the Earth. And the moon does not escape this fate either. In 5 billion years, roughly, the Earth will be baked and destroyed by the expanding sun as it becomes a red giant star, when it starts to fuse helium inside its core. When the sun runs out of helium, it starts to just fade away. So it sheds its outer layers and it becomes a white dwarf. So the sun, unfortunately, or I guess we should say fortunately, whatever, the sun just doesn't have enough mass to initiate a further collapse in order to get even heavier elements. The sun just turns into a planetary nebula. So it just kind of explodes out and just the outer layers just shed out into space. And then what's left behind is the core. The actual core of the star is now exposed to space as the outer layers are shed out. And so this is what happens when the sun runs out of helium. When too much carbon is built up in its core, it can no longer, it's not hot enough to fuse the carbon. And so it ends up just dying. And so this is the death of our sun. It ends up being about the size of the Earth, but it's a raw carbon core. In fact, carbon, when it's under high temperatures and extreme pressures, carbon turns into diamonds. And so basically the end result of the sun is a white dwarf star, which is essentially a gigantic diamond the size of the Earth. That's a white dwarf star. So that's the fate of the sun. But if the sun were larger, more than 8 times larger, then it could actually have enough gravitational energy, or we should say enough gravitational pressure from its larger mass that could actually collapse further. So if the red giant is massive enough, it'll collapse again, becoming even hotter, and then it can start to fuse carbon into even heavier elements. Here's a picture of the periodic table. And so as we track what we're going to do now is we're going to start at hydrogen and then work our way up the periodic table. So as long as we're down here below iron, fusion can release energy. And so as we start to build heavier and heavier elements within these most massive stars, energy is coming out, we're fusing together, getting bigger and bigger and bigger. But eventually we hit the bottom of this curve and fusion stops. Because if we continue to fuse, mass will actually be created, and so energy will be absorbed. But as long as we're less than iron, the star can actually get energy out. When the mass per nucleon decreases, we have a fusion releasing energy. But past that point, the mass per nucleon will increase, and so fusion will actually absorb energy. And that's the opposite of what you need for a star to be stable. So once the star hits iron, that's the end of the road. So nuclear fusion inside massive stars creates all the elements up until iron. Energy can't be released by the fusion of iron, and so the star dies. So what happens is once that core builds up enough iron, the star will actually collapse. There won't be enough outward pressure from the fusion because iron absorbs energy, and the whole star will just start collapsing down. And as it collapses, it actually ends up bouncing off the iron core, and then everything that was once rushing inward bounces off the core and then explodes outward in what's called a supernova explosion. So this is a picture of a supernova that happened in a nearby galaxy. You can see the supernova is down here, but that one supernova star shines as bright as 1 billion stars at the core of this galaxy. So in that instant, that flash of light from that supernova releases more energy than billions of stars in the core of this galaxy. This is one of the most energetic, awesome, and insane events that you can ever find in the universe, a supernova explosion. Remember how we said that iron stops? Well, the energy that comes out from this supernova explosion, there's actually enough energy now to start to fuse even higher, heavier elements. So past iron, fusion consumes energy. Remember, before iron, it releases energy. And so now there's so much energy coming out of the supernova that you can actually create even heavier elements beyond iron. And so this is one of the processes that's responsible for creating all the heavier elements. That stars slowly build up like factories up to iron, then they explode, and in their deaths spew out and build even heavier elements still. But actually, that's not the full story, right? Because dying low mass stars like the sun or exploding massive stars are making the green and yellow. So stars, when they explode, make the green and yellow. So this graph is basically showing you what percent of each element is coming from these different sources. Well, if we look at gold is coming from dying low mass stars, a very tiny bit, but most of it is actually coming from merging neutron stars. So there's actually lots of places where these elements are coming from. But if you look at this, all of these are from stars, except for cosmic ray fission, which is when high energy particles smash into the atmosphere of Earth, and the Big Bang fusion, which is the original creation of the universe, created those elements. But most of these elements on the periodic table are coming from stars. Well, except from the human synthesis, that there are no stable isotopes of these elements, and so you have to create them inside laboratories. So, stars will create them, but then they'll immediately fall apart. This is a picture of the Big Bang. So this is the beginning of the universe back here. And as time goes by, the universe expands. And so most of the blue stuff up here, hydrogen, helium, lithium. So all the hydrogen in the universe was created in the Big Bang. And a lot of the helium was as well. And a tiny little bit of lithium was. Most of the lithium that's around today is actually created when low mass stars die and spread out all the lithium that they created inside of them. This is a picture of a supernova explosion, and this is a picture of the cosmic rays coming in. This is another type of supernova. So the accretion scenario. So if you have like a white dwarf star, like a star that has died and it's orbiting next to a red giant star, the white dwarf can actually suck matter off the red giant star and then accumulate enough matter that it starts to fission again. And that can actually cause like a huge explosion, a supernova explosion. This is a neutron star merger, which is the pink stuff up here. So that's like silver, iodine. Like most of these elements out here were created with merging neutron stars. And so merging neutron stars actually create most of the heavy elements. They're created when a neutron star crashes, when they crash together. So here's a neutron star merger animation. We actually know that this happens. This was only discovered very recently by looking at the gravitational waves discovery. I actually mentioned that back in the very beginning of this course, back in August, in one of the very first lessons we took. So the neutron stars will spin around each other, and then eventually they'll smash into each other, and then that explosion, that massive neutron star collision, ends up having enough energy that you can create all these heavier elements. That's where all the uranium in the universe was created, was within a neutron star explosion. And so it's kind of funny to think about how a massive explosion between two neutron stars had to happen in order for us to make nuclear weapons with uranium. If you don't know what a neutron star is what's left over after a supernova. The leftover core of the star is a neutron star. So what does this mean? Well, this is the most exciting or amazing discovery in all of science, in my opinion, is that we are literally made of star stuff. Is that every atom heavier than helium was assembled by a star. So the iron in your blood, the oxygen that you're breathing, the carbon in the food that we eat, and all the atoms in your body were made inside stars. So we are, in a very literal sense, we are made of star stuff. Okay, that's it for this lesson. This is my final lesson, you guys. It's been a fun time in 9th grade physics, and I just want to strongly encourage you guys, if you thought any of this stuff was interesting and you want to learn more about it, take IB Physics. It's the class that I teach. I hope to see you guys there. Have a wonderful summer, and it has been a pleasure to be your teacher, and I will miss all of you profusely. Stay safe and take care. Bye.